Welcome to Glucose. Hey guys, welcome to Glucose. Today, we will talk about critical topic for medical students, which is action potential. First part of video about action potential, which is about 1,000th of a second, is the brief of reversal of electric polarization of the membrane of a nerve cell or muscle cell. In the neuron, an action potential produces the nerve impulse, and in the muscle cell, it produces the contraction required for all movement. In an action potential, the cell membrane potential changes quickly from negative to positive as sodium ions flow into the cell through ion channels, while potassium ions flow out of the cell. Before talking about steps of action potential, we will put a base by talking about cell state before stimulation, or what we called resting membrane potential. A neuron or muscle cell has a slightly negative electric polarization. That is, its interior has a negative charge compared with its exterior. This polarized state is created by a high concentration of positively charged sodium ions outside the cell and a high concentration of negatively charged chloride ions, as well as a lower concentration of positively charged potassium inside. The resulting resting membrane potential usually measures about minus 70 millivolts or minus 0.07 volt, the minus sign indicating a negative charge inside. Concerning generation of the action potential, stimulation of the cell by neurotransmitters travel across the synaptic cleft and bind to receptors, partially opens channel-shaped protein molecules in the membrane called sodium voltage gated channels. Sodium diffuses into the cell, shifting that inner part of the membrane toward a less negative polarization. If this local potential reaches a critical state called the threshold potential, measuring about from minus 50 to minus 55 MV, then sodium channels open completely. Sodium floods that part of the cell, which instantly depolarizes to an action potential of about positive 40 MV, causing depolarization phase. Depolarization activates sodium channels in adjacent parts of the membrane so that the nerve impulse moves along the fiber. If the entry of sodium into the fiber were not balanced by the exit of another ion of positive charge, an action potential could not decline from its peak value and return to the resting potential. The declining phase of the action potential is caused by the closing of sodium channels and the opening of potassium channels, leading to potassium efflux, which allows a charge approximately equal to that brought into the cell to leave in the form of potassium ions, causing repolarization phase, which ends the action potential. At a particular spot on the neuron's membrane, there is a continued efflux of K+, causing cell's membrane potential more negative than resting membrane potential, causing hyperpolarization phase. Subsequently, protein transport molecules called sodium-potassium pump start to pump sodium ions out of the cell and potassium ions into the cell in ratio 3 sodium ions to 2 potassium ions. This restores the original ion concentrations causing resting state and readies the cell for a new action potential. After neuron has fired an action potential, another action potential cannot be easily produced, which is a state of recovery called refractory period. This encourages unidirectional flow of action potentials. Sometimes action potential is called a propagated potential because a wave of excitation is actively transmitted along the nerve or muscle fiber. An action potential is conducted at speeds that range from 1 to 100 meters, 3 to 300 feet per second, depending on the properties of the fiber and its environment. In myelinated axons, propagation occurs via saltatory conduction because in myelinated neurons, ion flows occur only at the nodes of Ranvier. As a result, the action potential signal jumps along the axon membrane from node to node rather than spreading smoothly along the membrane, as they do in axons that do not have a myelin sheath. This is due to a clustering of Na+ and K+ ion channels at the nodes of Ranvier. In unmyelinated axons, propagation occurs via continuous conduction. Because in unmyelinated axons do not have nodes of Ranvier, and ion channels in these axons are spread over the entire membrane surface. In the second part of video, we will talk about transmitting nerve impulses. The place where an axon terminal meets another cell is called a synapse. This is where the the transmission of a nerve impulse to another cell occurs. The cell that sends the nerve impulse is called the presynaptic cell, and the cell that receives the nerve impulse is called the postsynaptic cell. Some synapses are purely electrical and make direct electrical connections between neurons. However, most synapses are chemical synapses. The transmission of nerve impulses across chemical synapses is more complex. At a chemical synapse, the presynaptic area contains many tiny spherical vessels called synaptic vesicles that are packed with chemicals called neurotransmitters. When an action potential reaches the axon terminal of the presynaptic cell, it opens channels that allow calcium to enter the terminal. Calcium causes synaptic vesicles to fuse with the membrane, releasing their contents into the narrow space between the presynaptic and postsynaptic membranes. This area is called the synaptic cleft. The neurotransmitter molecules travel across the synaptic cleft and bind to receptors, which are proteins that are embedded in the membrane of the postsynaptic cell. The effect of a neurotransmitter on a postsynaptic cell depends mainly on the type of receptors that it activates, making it possible for a particular neurotransmitter to have different effects on various target cells. A neurotransmitter might excite one set of target cells, inhibit others, and have complex modulatory effects on still others, depending on the type of receptors. However, some neurotransmitters have relatively consistent effects on other cells. Finally, concerning cardiac action potentials, they are generated by pacemaker cells located in the sinoatrial node and atrioventricular node. These cells do not need a stimulus to generate an action potential. That's all about action potential. Thanks for listening, and see you guys in the next video.